Hello and welcome to January 2022 Plumtree Online. Tonight I'm going to talk about the amateur astronomer's sky, and this is really pitched at people new to astronomy. I've had several questions about this topic, so some of the more seasoned astronomers may not enjoy this as much, but watch and then you can ask questions anyway. So, amateur astronomy, this is one of my telescopes, the Celestron C11, and unfortunately that's not my back garden, that is Wales. So astronomy is lovely to be outdoors, and it's a hobby, and the definition of a hobby is an activity which is regularly done in one's leisure time for pleasure. But Patrick Moore always used to say astronomy is one of the scientific fields where amateurs can and do make real scientific contributions. So this is the expanding universe theory. We're not going to talk about any theories or cosmology, astrophysics. This is just amateur astronomy tonight. It's all stuff involving eyes, telescopes, those sort of things. So I thought I'd structure it around the main sections of the British Astronomical Association, and the main sections are listed here. I'm not necessarily going to cover these in order, and I'm not necessarily going to cover them all, but I've used this as a template to try and pull out as many different activities that the amateur astronomer can undertake as possible. So the atmosphere, we live in the Earth's atmosphere, it's all around us and it influences what we do. It's where all the weather happens, and man has had a long interest in studying the atmosphere, studying the weather. And in Victorian times, wealthy, mostly gentlemen, would have observatories and they would study astronomy and study meteorology. And here we've got a picture of the Radcliffe Observatory in Oxford, and this was one such site where we've got astronomy happening, not necessarily in this building, but at the site, and then we've got a meteorological setup as well. And if we think about the Earth's atmosphere, several things happen here with interest to the amateur astronomer. And I've listed them here. We're just going to briefly whip through them. So the first is something called noctilucent clouds. These occur in the summer mostly in the Northern Hemisphere, so June, July mostly. They occur at night. In the summer, the nights are short and the sun is below the horizon down here, and the light from the sun is shining up and it's illuminating these ice crystals, clouds. And over time we observe how far south these clouds can be seen, and that data can be used to study what's happening in the atmosphere at the levels where these clouds are. Now, something much more commonly or more widespread known about are aurora. This is the solar particles coming in, interacting with the Earth's magnetic field and being filtered down through the poles. We've got aurora borealis, the northern lights, and aurora australis, the southern lights. So that they're coming in both poles and activating gas molecules in the atmosphere and causing these exquisite lights. There's some specific features of the aurora which are of interest to amateur astronomers as well as scientists, and one of these are these proton arcs. It was given a name Steve some time ago, and they've retrofitted an abbreviation for it. So it's a strong thermal emission velocity enhancement. And you can see this kind of jet of auroral activity. And these are not very common, but they are observed. And it seems they were first observed or first recorded in the late 1800s. So clouds are pretty bad for most astronomers because they block out the sky, block out a clear path to see the stars. But clouds can be very pretty. Here we've got some daytime cloud iridescence. So this is refraction of light, and it causes this rainbow effect. And there's all sorts of atmospheric effects you get with refraction of light. Here we've got a circumzenithal arc, and you can just see this sort of inverted rainbow, which is up near the zenith, so right overhead. And these are often associated with other features. And I've expanded this image, which on a wheeler allowed me to use. And you can imagine the sun is there. And then we've also got this arc going around the sun, so a sun halo. And then if we take that a step further, we've got these little condensations of light. These are sundogs. And then if we look even closer, there's another wider halo, the so-called Parry arc. I didn't know it was called a Parry arc until I was researching this talk. And we've got this inverted feature as well, like an arc going the other way. And all of these are mapped out in this illustration. And here we can see, here's that Parry arc, and then this inverted arc-like feature, this upper 22 degrees tangent arc. So you don't have to have any fancy equipment to study these sorts of features. You can just, if the weather conditions are right, you can just get out there and observe and photograph or sketch them. A bit more refraction of light, double rainbow. Here's what taken at the observatory. So the observatory's over here if you've not been. And here we can see the inner rainbow and then the outer rainbow. Another thing which happens in the atmosphere are meteors. Here's a meteor that I captured. So this is a piece of debris floating around the solar system, which at some point interacts with the Earth's atmosphere as it comes careering in, and the interaction causes the particle to heat up, excites molecules, and we get a flash of light or a streak of light. And this was just taken with a static mounted DSLR camera. Take longer exposures. Meteors can be quite difficult to pick up, but they're pretty when you see them. Here we've got a video shot from Alex Pratt of a Geminid meteor. This is on a dedicated meteor camera. The frame rate's probably about 24 frames per second, and this is slowed down so it would be quicker. And you can see here the Pleiades constellation, Aldebaran, and then Orion the Hunter would be down here. And this sort of information can be used to work out where that meteor's come from, looking where it's emerged from in the sky, its trajectory. And if you get various people with meteor cameras, you can triangulate and get orbital paths for these events. And this is a picture of someone's meteor array setup. So they've got lots of cameras on the shed outside pointing at different parts of the sky. And over the course of the night, they'll be triggered by flashes of light to record video, and then that can be examined and the meteor paths worked out. So during the Second World War, radio receivers and transmitters were used to work out or track aircraft and the doodle bugs, the flying bombs. And this is a picture from Richmond Park in London. And here's an old radio receiver. And what the scientists found was, as well as finding aircraft and the like, there was occasional blips, radio blips, and they worked out that when meteors were interacting with the Earth's atmosphere, shooting through the atmosphere, the excitation caused the release of energy, and some of that energy was picked up as a radio blip. And people went on, and now amateurs can do radio astronomy. This is called a Yagi aerial. It's just copper pipe linked up with a wire. And instead of looking for the blips of meteors, which are very small bits of dust interacting with the atmosphere, what amateur astronomers in radio now do is use radio signals which are transmitted from Earth, and these shoot up to the atmosphere, and when a meteor comes, it reflects or deflects that radio signal and it can be received. So this is any transmitter. This could be a radio station which is being broadcast, and the receiver just listens for that radio signal. It can't normally hear it because it's below its horizon, but the meteor deflects that signal. And this can be used to observe meteors in the daytime. So we can't see the flashes of light, they're too faint in the daytime, but certainly with radio meteor detection, you can do this in the daytime. And people have used radio and tied it with optical or light data, which is quite fascinating work. So there's lots of things to be done in radio astronomy. Storms on Jupiter can be observed by amateur equipment, solar activity, meteors as we've seen, and mapping of the Milky Way, something called moon bounce, sending a signal out to the moon, and timing how long it takes to come back. And then people also do surveys of the sky, looking for high energy bursts from various sources. So if we go outside of our atmosphere now and think about our solar system, so our family, we've got the sun and the planets and the asteroid belt, and there's comets and moons. And this is a lovely montage, I should say, by Gareth in the Society. And he's taken all these images, not in one shot, but it's a composite image. And we've got Mercury, Venus, no picture of Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. So you have to remember, observing the sun incorrectly can cause permanent visual damage. So that's always something to be careful of. So if you've got a small telescope, one way to observe the sun is to form a shield around the outside of the scope and do something called projection or image projection, and project the image of the sun coming through the telescope onto a flat surface. And you can see here the sun's projected, and you can see these dots of sunspots. Again, you need to be careful and know what you're doing, because if the finder scope is still attached, that can pick up the sun and cause burns. So anything with the sun, do make sure you know what you're doing. Now the other thing to do, looking at the sun with relatively cheap kit, is to build one of these solar cans. And we did this at Plumtree a couple of months ago. So this is a can which has been cut open, and there's a sheet of photographic paper inside, and then it's been closed and taped up. And you can just see there's a pinhole in the can, and it's been fastened to something sturdy, and it's pointing south. And what will happen is we'll leave it there for 6 months, and then when we process the paper, you'll see that you end up with a solar graph. And here we can see the sun's path every day. It's risen in the east, reached its peak midday, and then it sets in the west. And you can imagine here this is winter because the sun isn't up for very long. And then this will be summer where the sun's up for a much longer period of time. And David Buxton, one of our members, sent me this. He's recently processed his solar can, and this must be at the front of his house because I think that's his road, and that must be the house opposite. And again, you can see the winter sun and then the summer sun, which has been clipped off. And he tells me he's put another couple out and altered the angle. Now you can look at the sun with a telescope using appropriate filters, and this is with a white light filter. And you can see, this was a few years ago, you can see some sunspots. So this is relatively easy to do if you've got a telescope. Again, you need to take suitable precautions. And here on the right, this is with a white light filter of the photosphere. And on the left, Alan Friedman has cleverly cropped one half of the sun in white light and the other in so-called hydrogen alpha. So this is a very narrow band wavelength of light, and this shows up the chromosphere. And you can see he's done it cleverly as well to show that it is higher, it sits higher than the photosphere. And hydrogen alpha can show a lot more details. We can see here, here's a sunspot in hydrogen alpha. We've got the black umbra, and then the grey penumbra around it, and then these sort of filaments drifting off. Now the sun rotates. Most things in the solar system rotate on their own axis. I'm sure someone will pick me up for some things in the solar system which don't, but the sun does this, so it spins, and this is an animation showing how the sun spins and how the sunspots change through the course of the day. And the sun, because it's essentially a gas or liquid body, the equator spins at a different rate to the near the poles. So the equator spins in about 25 days, one rotation, and about 35 days at the pole. And the interest in sunspots is over long periods of time, we can see trends. So we've got 1870 here to 2022. And what happens is, this is called the butterfly diagram. And the sunspots, over a sunspot cycle, so a cycle is about 11 years, sunspots start nearer the pole, so the North Pole's here, South Pole's here. So they start at about 30 degrees north and 30 degrees south. And over the period of the sunspot cycle, the sunspots drift nearer the equator. And then there's a period of solar minimum, and then it starts again. The sunspots appear at 30 degrees plus minus the equator and drift nearer. And if we plot sunspot number, you can see they peak. And that's this so-called solar cycle. And this is linked to weather, climate, and all sorts of things. Probably mood as well. Here we've got another feature in hydrogen alpha, is a solar prominence, one of Pete Lawrence's pictures. So this is an eruption as such of gas and plasma away from the surface of the sun. Nicely captured, and people do animations, videos of this over a period of minutes. You can see an eruption happen and then it claps back down. So apart from the sun in the solar system, we've also got the planets. I always show this image because I love it. This is my a time-lapse animation of Jupiter rotating, and you can see the red spot. But then if we look at a picture by Damien Peach, probably the best planetary imager in the world, I imagine, you can see his amazing image of Jupiter, and if you put it next to mine, well, mine's all right, but this is just very, very good. And there's lots of reasons why his images are good. He's got nice equipment, he knows how to use it, and also he goes to climates where the climate is more favourable to observing planets. So he'll go to nearer the equator where there's less turbulent air than we have in the UK. Now here we've got Damien Peach's image on the left and an image from Voyager 2 from 40 years ago when it was flying past Jupiter. And the image from Voyager 2 is the distance was about 350,000 miles. So that's 1.5 times the distance from Earth to the Moon, say. And Damien Peach's image, which I think is nearly as good, was taken from Earth through the atmosphere of Earth and at a distance of 500 million miles. So there's a over 1,000-fold difference in distance. So it's pretty amazing what can be achieved for planetary imaging from the surface of the Earth. Here's some other planets that I took, Mars on the left and Saturn. And here's a series of images of Saturn by Damien Peach, showing the rings as they appear to us on Earth throughout the orbit of Saturn around the Sun. And the angle of the rings changes because the orbit of the Earth and the orbit of Saturn aren't on the same plane. So we get to look above the rings sometimes and below the rings at other times. And this just shows a period of 2004 to 2015. And in a few years, we'll have face-on rings again. The other planets in the solar system, Mercury, very small, pretty hard to image. Venus, this is one by Richard Seven, lovely crescent shape, and you can see the horns, the cusps of the planet, and you get the impression, although it isn't there, you can imagine it is a whole circle. Uranus, this is a drawing by Paul Abel. So if you don't have cameras, you can draw things. And also Neptune, very difficult to image because it is so small and so far away, relatively small. And finally, although it's not a planet, here is Pluto. This is an animation of 2 images a day or so apart. You can see it moving. Moons, so our moon is about 3,500 kilometers in diameter, and that's one of my most favorite craters, Plato. Here we again, another Damien Peach image of Plato. It's about 100 kilometers in diameter. So if you imagine Nottingham's at one end and Bedford's at the other, so it's pretty vast, and it's got a very flat bottom. It's got these lovely craterlets at the base of them, and you always know when you've got good seeing if the atmosphere is relatively stable, if you can make out those craterlets. And if this was a train line, Nottingham to Bedford, then this craterlet would be Kettering. So occasionally our moon obscures the light from the sun, And this is a time lapse of a partial solar eclipse I took in 2015. The image isn't very stable for various reasons, mostly because of my processing skills. But you can see the moon is drifting slowly in front of the sun and occluding much of the light, and then it goes all the way through, and you can see a crescent sun. And I'd forgotten how extensive this eclipse was. They are very weird events. I've never seen a total eclipse, but it's on my list of things to undertake. You can see that sunspot's now been revealed and the moon is drifting off, and then that's it, the moon's gone, and then the cloud starts. So I was very lucky. But there are other moons in the solar system as well. Here's Jupiter's the bright spot, and then the 4 Galilean moons. And here's again another Damien Peach image of Jupiter, and then Ganymede and Europa, the moons. And you have to imagine that the sun is over here, and it's casting the shadow of Ganymede and Europa onto the surface of the planet. And this is a shadow transit, so over time you would see the shadow move as the moons move. And then we've got Uranus. Martin Lewis is another very excellent planetary imager, and he's got various moons of Uranus, which is very hard to do. Now, another family of things in the solar system are comets. So these are ice balls with dust and bits of debris left over from the early solar system, and they orbit around the sun, and as they get near the sun they heat up and the volatile agents come off and form a tail. And one of the best comets I think in recent years has been Hale-Bopp, and you can see the comets commonly have 2 tails, a dust tail and an ion tail. And here we've got a comet from, well, not so long ago. This was just a month or so ago, Comet Leonard, and this is a time lapse over about an hour of the comet passing over the globular cluster M3 by Mazin Younis, who lives in imaged this in southern Morocco. And you can see again the head of the head of the comet, and then the tail coming out. And you can see that it's moving at a much faster rate than the other background stars. So over a period of an hour, you can see significant movement. Now, I think the last family of objects in the solar system are asteroids. And again, another one by Mazin. We've got here a time lapse of an hour or so, probably less, of an asteroid moving. And I did spot another one earlier. Yeah, I don't know if there's another one just down there for the keen eye. Now, this asteroid is called 4678 Ninian. And what we know is there's various websites, but this is what 4678 looks like. And you can see physical data about it. Its orbital period around the sun is 3.4 years. It's got its rotation period, and also its albedo, 0.17. And that's actually, it's more reflective, or it reflects more light than the moon, than Mars. And when I was looking up about the albedo earlier, it's very similar to Pluto. So because Pluto's got all that ice on the surface, it's much more reflective than our moon, say. And this website also shows the orbital path of 4678. And you can see it's outside that of Mars and will be inside that of Jupiter. And it's offset, which is very common for asteroids and comets. They have quite an elliptical orbit, unlike the planets, which are usually a bit more spherical. So if we think now outside our solar system, but within our galaxy still, so if this is a representation of our galaxy, the Milky Way, we live somewhere out here. We can't actually see the Milky Way in this perspective, so this is just another galaxy which we think probably the Milky Way looks like, a spiral galaxy with arms. Now this lovely animation, this again shows a pictorial representation of the Milky Way, and the sun is amongst these blue dots, and all these things near us, relatively near us, are the open clusters, planetary nebula, diffuse nebula. So most of the things we observe as amateur astronomers are pretty close to us in our galaxy. And then we've got other Messier objects much further away, but still within our galaxy. And these are mostly globular clusters. And we'll see a picture of those in a moment. I think, yeah, it does tip up. So the white dot is the sun, and it's just there. So you can see now that the open clusters, planetary nebulas and things, certainly in the Messier catalogue, are pretty close to us. They're not that far away. When I say pretty close, they're still several light years, many light years away. An M54 is a globular cluster, and in fact, I've read it's outside the Milky Way. It belongs to another galaxy. So here we've got a globular cluster, M13. So this is a group of stars that are gravitationally bound. They all kind of stay together. They're pretty old, but they're very easy to find with binoculars and a small telescope. And a lot of research goes into globular clusters, working out their age and the gravity. Here we've got the open clusters. So this is a lovely picture of the Pleiades, or the Seven Sisters, by Gareth. So these stars are related to one another, but less tightly bound than in the globular clusters. And this patch happened to probably be drifting through some gas clouds, which they're illuminating, and that gives us this nebulosity. And then we've got other forms of nebula. So this is the Great Orion Nebula. I'm not sure how well that's showing. So this again can be seen with binoculars. It's pretty bright. Let's say not very bright, but bright enough to be seen with binoculars, and is a lovely target for astrophotography. And here we've got an image by Marcus Stone in the Society of the Horsehead Nebula and the Flame Nebula. So you can see the horse, it looks like a horse's head or a seahorse. This is a bit harder to see, easier to photograph. And then we get to really fancy imaging, the stuff that Lee does. So the Elephant Trunk Nebula. This is in mostly hydrogen alpha, and the Bubble Nebula by Lee. And then back to basic imaging by me. And we've got Planetary Nebula. So this is the Ring Nebula, M57. And the star in the center has thrown off this matter, pushing it out. And that's what we see. The Crab Nebula, Messier 1, again by Lee. This is a supernova remnant. So a star that's gone supernova and pushed out all this stuff, and it's got this odd sort of fibrils and pattern, fibrous kind of looking nature. Looks more like a sponge than a crab, I think. And there are other forms of nebula in the Milky Way. This is a dark nebula. This is Barnard 7. So this is patches or big areas of gas, dust, which is obscuring the light of stars in the distance. And Barnard is famous for the study of and cataloguing of dark nebula. They're quite interesting, and we definitely should do a plum tree on them, although it would take a lot of research. Julian, we've got to do dark nebula. Now, the other thing amateurs observe in our galaxy rather are double stars. So a lot of stars are doubles, so they're paired with. There's a pair rather of stars. They associated with one another, orbit around each other, or have a common center of gravity. And amateurs like to try and split doubles, so see if they can see the fainter one. And here we have Gareth and Richard. A couple of years ago, were having a go with Sirius, the dog star, and they managed to find a much fainter companion star, which is called the Pup. So that's pretty difficult to do, and I think they did really well to do that. Now, a lot of things in the galaxy are so-called variable, so their light intensity changes over time. This can be due to various reasons. We've had talks on variable stars before, but here we can see along the y-axis we've got magnitude, so brightness, and we've got time along the bottom. And Graham Coates here is with a camera and software has worked out the light intensity of this star in Hercules over a period of time. And you can see the star gets dimmer and brighter and dimmer and brighter. So lots of stars are variable stars, and variable star astronomy is a massive area for amateurs to be involved with. Stars vary at different rates. Some are very slow, some are quite rapid. And it's the time along the bottom is Julian date. Now, as I say, there's lots of variable things in the sky. Another one is recently not so recently, but exoplanets. Exoplanets have been known about for some time, and here we've got an animation of a distant star, and it's got a planet orbiting it. And you can see that if we were to measure the light intensity coming from the star, it dips as the planet absorbs or stops some of that light reaching us. And this is called the transit method of observing exoplanets. And amateurs can get involved with this. And in fact, this is our treasurer, Mike Provo, with his Unistellar telescope, has done some transit work, looking at specific exoplanet system. And here you can see his data is been smoothed out with the red line, and his raw data is shown here as well. And you can see the planet isn't in front of the star, and then the planet comes in front of the star. It transits the face of the star, and then it comes off the limb again, and the star returns to its baseline brightness. So amateurs can easily identify exoplanets or study existing exoplanets. And Mike wanted me to make sure that the work of Thomas Esposito and the team was mentioned because they did the analysis of Mike's data. Now, Our galaxy is called the Milky Way, and I said earlier we couldn't see it as a disk with arms, but we can look at it in one way, and that is looking at the night sky and seeing this sort of line of stars, of brighter area of sky. And here, this is one of the astronomers from the European Space Observatory has taken a lovely picture of the Milky Way. And if you can imagine, this is us from, let's go to the next slide. So we're out here in our disk, and we're looking in towards the center of the Milky Way. So we're outside and we're looking at the Milky Way edge on. And the galactic center is around here. So we've got the galactic bulge, and then the arms, or the expanse of stars drifting away from the galactic center are out to the side. So that's everything in our galaxy. What about outside? Well, I don't think there's three-eyed little green men. Well, there may be. But our nearest major galaxy is the Andromeda galaxy. Nice picture by Damien here. And this is pretty similar to how the Milky Way would look if we could look at it from a distance. And there's lots of galaxies that amateurs observe. This is one that, again, Mike Provo with his unistellar scope has detected, and the Whirlpool galaxy, which is actually two cores, and there's material being pulled off the smaller one onto the bigger one. I think it's that way. I might have questions saying it's the other way. And then there's clusters of galaxies out there. So these gravitationally interacting galaxies. This is the Virgo cluster, an amazing cluster of galaxies, mixture of types of galaxies. And then here's an image of M81 and M82 taken by me. It's not a great image, but it shows the two galaxies, and there's even a little another galaxy here. Now, I always get these M81. So this is M82. Looks like a cigar. And this is another image I took of M82. And these two red lines are, I don't think it's displaying particularly well, but are pointing to this white dot here. And so 4 or 5 years ago, there was a supernova in this galaxy, and a star erupted and became very bright, and we could see this supernova as a brightening of the star, and that's what I took this image for. And then over time that will fade back down, and there won't be a patch of light there anymore. So I've largely run out of time, I'm sure. I haven't covered most things. I haven't talked about anything to do with spectroscopy or variable nebula, largely because the nicest variable nebula I can't pronounce. I haven't talked about satellites or artificial satellite imaging, nova patrols, archaeoastronomy, that's a fascinating subject, the use of remote telescopes, and history of astronomy, which is something I'm interested in, and as are other members of the society. And the last image is actually Martin Lewis's International Space Station. So again, I'm just in awe that someone can push a telescope and capture the data quick enough to get enough data to process to show the structure of the space station flying above our heads at whatever it is, 450 miles above us in space. So that's it. Let's open to questions and a bit of chat. Thank you.
Okay, thank you, James, for that resume of what the amateur can do and see in the night sky. It's really good. We'll open up for questions. So if you want to put those into the live chat, then please do so, and we'll pick those up. And please say Julian's with us as well this evening to field some questions. So we've got a good team on tonight if anyone wants to send any through. So evening, Julian. Hope you're well.
Oops, technology failure. Yes, here I am. Thank you.
Good. I'll put the questions up on the screen.
Oh, there's already one there for James.
Not for me. I can take the observing questions.
So what makes the planet spin?
Do they all
And
spin
do the
anti-clockwise?
deals.
Well, they don't all spin anti-clockwise. Venus spins backwards, I think. That's correct. And is it Neptune that spins on its side?
Oh, Uranus.
Uranus. Oh, one of those
Yeah.
things a long way away. Yeah. I think they spin because that's how they're formed. They have a initial bit of spin, but as they collapse in, they spin up as they go, as they accrete more stuff. So it was the stuff they were made from was already spinning, and it's just amplified as they come together. Ooh. Did you see the asteroid the other night, James?
No, it was foggy, wasn't it?
Quite probably. It usually is.
I'm trying to remember which day it was, but one day the asteroid, I think it was foggy.
Wasn't particularly close, was it? It was beyond the moon. Oh, right. Well, I got the right one.
Yeah, it was 300,000 miles away.
Right, so that's beyond the moon.
Yeah.
So we didn't have to duck. That's good.
No.
I got a question on the plot on, I think it was the 3D galaxies plot, and it showed various like messy objects open clustered, and they're projected up away from the plane. Was that just for the graphic, or is that genuinely where they are relative to the Milky Way?
I think they were mostly globular clusters, and they are away from they're in their own little halo around the galactic bulge. So
they weren't sitting, they don't sit within the plane in the Milky Way then, that was their genuine positions.
Let me find the slide.
I think there's a couple that do, but most of them don't.
Right. They just seem very high up on that graph, so I thought that seems a bit surprising.
They're perhaps put there for emphasis or something.
I thought so, yeah. I thought I'd ask.
That website, you can put your own data in and form things.
Oh, there's a tricky one from David Dunford. That's definitely you, James.
I haven't seen it. I was trying to find the Galaxy software. What's the question?
If I bought a solar scope, what long-term observing program could I adopt to justify its purchase rather than it gathering dust after a few weeks?
Well, you could certainly do sunspot counts, observation and imaging of the activity. So the solar flares. Was there a time lapse of a solar flare in the talk? I don't think there was.
No, you mentioned it, but I don't think there was.
They are really fascinating. I mean that's mostly it. The activity, sunspots, and the two types of quark scopes. One looks at the chromosphere and looks for granulation in more detail, and the other type looks at prominences. So if you're looking at the quark type, there's two types, so you need to determine which you're more interested in. But most of the Lunt and the other ones are just expensive and very nice.
The good thing about solar observing is you don't get quite so cold, and and it's quick. You don't have to take long exposures.
No. It's still heavily influenced by seeing. If the seeing is poor, then the view in HA can be pretty poor too. You need a nice seeing, transparent day, and the more you can spend, the better. I mean, if you can justify it, the Lunts, sort of the double stacked ones, are really the bee's knees. But I think are about £4,000 or so. You just have to sneak it past Mrs. Dunsford. She'll never know.
How much are the Coronados these days?
I don't know. I would have to look online.
Yeah, I think they're less than that.
Right.
What else have we got? Did anyone have any joy with the quadrantids? Stuart saw a couple.
No.
No.
I didn't. No.
Another one. What a great presentation. I want to know what size telescope you use to capture the Virgo cluster.
So that wasn't my scope. That was I'm trying to. It's so the cluster is quite an extensive thing. There's some people image just part of it, and then you actually need a very short focal length, well, not very short, but a short focal length telescope to get all of it in, because it's spread out over quite an area. And with astrophotography, aperture isn't really necessarily the be all and end all. For deep sky stuff, you really want a very good tracking mount, and an 80mm refractor will be sufficient. But I don't know what scope that was.
Okay, there's a few more questions. So lots of people saying how good you are, James.
Ah,
You knew that.
well, most of the good images aren't mine.
David Turner says there seem to be more sunspots in the 20th century than 19th century. Is there any suggestion that the sun is emitting more energy than previously? I think sunspots are quite variable, aren't they? Nobody quite knows what's going to happen, so it's always a surprise.
Yeah. Well, Richard, have you got the? Can you put up the sunspot plot? Or no?
No.
Let me try and. I'm flicking through slides frantically trying to find. Ah, there. Can I share screen?
Yep.
Richard's nodding. Richard despairs at me. This will stop other people sharing. That's fine. And then I'll share that one. Can you see the sunspot cycle?
Yes, indeed.
So you can see that over time there is variation. See, within each sort of block of period of 22 years or so, you've got a peak, a maximum and a minimum, maximum, minimum, and then over long periods of time, those maxima do get increased. So yes, there is variation. As to why that happens, I've no idea. Julian, it's his department.
I don't think anyone knows. That's the good thing. Well, that's the bad thing. Well, nobody knows yet. But we have Solar Parker Probe, and I forget what the other one is.
Bepi? Oh no, that's Mercury.
There's another solar one that's doing stuff, so we might get more info soon.
I guess we're a bit restricted with that in terms of the observational record, aren't we? We can't go further back, presumably, than what we've got observational records for. I guess it's not like some of the, you can project or look at climates and atmospheric content going back quite a long way through ice core records and all sorts of things. But with sunspots, I guess we are restricted to when
quite a way.
Sunspot observations were taken.
I think Galileo recorded some. I don't know how thorough he was though.
Yeah, and they have been recorded when looking through cloud and mist. Can you still see my screen?
Yes, we can.
So this is Graham Coates of the BAA, who did that lovely image of the Virgo cluster. Yeah. And so I'm just looking to see what scope it was. So yeah, it was an 80mm refractor. It's got quite a fancy camera, but it's quite a relatively wide field of view. If we use the observatory telescope, we'd only get sort of a couple of these things in. Yeah. I can't remember. But look how many there are. It's just amazing.
Yeah, plenty to go at. We're a member of the Virgo cluster. Well, we're distantly related to them, aren't we? I think that's our nearest cluster.
So how much observational data does the department at the university use on galaxy work? I mean, do you look at images like this and think about the gravitational forces and the evolution of these sort of things, or is it much more just mathematical and modeling?
No, they certainly, quite a lot of them just analyze those sorts of pictures, probably further away than that, because kind of a lot of the local stuff's been done, so difficult to get research out of nearby stuff. Mike Merrifield does stuff with Andromeda and other places, so that's quite near. Well, that's very near. So yeah, they would generally look at how the light varies across those galaxies and classify them and things like that, using computer software mostly. Got any other questions? Shirley thinks archaeoastronomy sounds good.
Oh yeah. So Dan Brown at Nottingham Trent University is very interested in archaeoastronomy.
Yeah, we should get him in for a talk. So that's, yes, Alan's asking what is archaeoastronomy. So it's what is it, James?
Well, there's various components to it. One is sort of more archaeology, so looking at astronomically related structures built by man, so Stonehenge, other henges, various rocks with holes down in Cornwall and places that people would project the summer sun through and things. And then the other side is rolling back the clock with software like Stellarium and trying to piece together because everything moves in the sky slowly over time, if the alignment of, say, Stonehenge is on a different star than it might align with today. So it's using software to wind back the clock, how the sky might have looked 5,000 years ago, and seeing if structures or beliefs or whatever tally up with that. And I know Dan Brown did some work. He gave a talk, I'm not sure if it was to NAS or at NTU, about caves which had been dug into a mountain for burials, and they were aligned to something in the night sky at that period. Cave burials.
Yeah, he said some of the entrances are sort of aligned with stars and things like that.
Hopefully Dan Brown's not here, so he doesn't realise I've forgotten what they're aligned with. Sorry, Dan.
What else have we got? Shirley says, sunspot cyclic, and then, I see. So she's answered her own question. Very good.
Right.
James said, could we show some early JWST, I presume, things? I don't think JWST is going to be doing very much imaging till about the summertime. There might be a few test images taken before then, but I think they have like a 4 or 5 month calibration and all the rest of it before any data. I've just found I was doing a class today with Omar, one of the professors at Nottingham, and he's on 2 teams that are getting early JWST data. So I might get him to come along and give a talk. Once he's got this. No point before.
No. Talking of JWST, Richard, I've got up the data that we took of JWST.
Oh yeah, show that.
Well, I'm embarrassed because it's so awful.
Well, it's amazing you got it at all. It's a long, long way away and very, very faint.
And everything's out of focus, and this has got lots of hot pixels.
Oh right, yes.
So, can you see my pointer?
Yes.
So, I won't know until I start clicking through, but JWST is somewhere around here. But unfortunately, all the other stars move a little bit as well, and JWST will drift off up here. So I'll just click through them once I've clicked on one. Is it showing that it's drifting
yeah,
up?
I can see it, yes. But it's sort of staying still while everything else drifts down.
Yeah.
Oh, very good.
So that is the James Webb Space Telescope.
Worth 9 billion of your pounds. Oh, that's really good, that is, yeah.
Well, it might be an asteroid. Richard might have given me the wrong coordinates.
He wouldn't do that.
Been very unlucky if that's what we picked up. So that was with the C14 at the observatory.
Yeah.
And it was, very faint, wasn't it, really?
Yeah. It's either JWST or asteroid on collision course with Earth.
Yeah. So, it was a bit of a rush job. So I hadn't set the camera up properly, and but we got it. So we're very pleased.
No, it's very, very amazing job. Because it's what magnitude was it?
It was about 15 at that point.
Wow, so that's like Pluto.
Yeah, yeah.
So yeah, very well done.
Are there any other questions?
Owen asked, how is distance to deep space objects calculated? How will astronomers know James Webb Telescope is oldest objects? Well, that is a huge topic on its own. So I think we should have a plum tree one on distance, how you measure distances, because it's complicated. So yeah, great topic. Anything else? Just looking around. No, I think that's it. I think we've exhausted everyone. Well done, James.
There's just one at the bottom for Alwyn. How is the distance to deep space objects calculated?
Yeah,
We've just done that
I've just
one.
done that one.
Which has
Richard's on
got
a short. He's on a short delay.
COVID brain. Right then. Well, that's good.
Very good. Yeah, thank you for doing that, James.
That's all right. What's the next formal meeting?
Right, the next formal meeting is, I've forgotten.
Oh,
be on the screen in a second. Here it comes.
There we are. Phil Evans from the University of Leicester doing astronomy without light. So he's looking at, I think it's multi-messenger stuff. So I think it's to do with that. I did hear him give a talk somewhere. So it was either the RAS or somewhere. So Leicester, that's very close. And then we can't meet in person anyway. So anyway, should be interesting on how you do astronomy without using light. Then yeah, next one after that, planets, exoplanets. Professor Don Polacco, he's one of the top exoplanet people pretty much in the world. So he's going to come and give us a talk on the state of the art or state of the universe as exoplanets. That should be good too.
Cool. Shall we wrap up there?
Yes.
I think.
Thanks, James, for doing the talk, and for Julian for joining us for questions. Before we finish then, obviously just for members who haven't yet rejoined, we're into the new membership period for 2022. So thanks to everyone who has already joined. We've had quite a lot of members already rejoined, but those who haven't, you've got a 2 months left to join. So you should have had your renewal notices through. So they're the prices for adults £30 and partnership £45 and students £5. And if we've got any non-members that are watching this evening, then we'd love to welcome you to the society. If you go to the website, the details of how to join are on there on the membership page. So if you do enjoy the meetings, then do join us. Hopefully we'll be back face to face in March, but we'll confirm that. So as Julian said, the next meeting is going to be on YouTube in a fortnight's time.
Roy has said, will the next plum tree meeting be in person? I think we're going to see.
I've just typed, we'll see. We're playing it by ear still at the moment. Yeah.
We'd like to, but we'll see where we are at that time.
Yeah.
Great. Okay. We'll say good night to everybody. We thought we'd finish tonight just to show the video that we produced, basically showing what the Society got up to in 2021. So we'll play that to finish tonight. So thanks again to James for doing the talk, and to Julian. So we'll see you in a fortnight's time. So good night, everyone.
Is the cosmic microwave background expanding for us? Well, I think the conceptual difficulty that most people who haven't studied physics, astronomy, cosmology have is they think of the Big Bang as an explosion within space, that space exists and the Big Bang happened and everything's moving apart. Whereas in fact, everywhere in the universe was at the Big Bang during the Big Bang. Everywhere was in the same place. and everything's moving away from everything else, but it's not moving through space. It's the space itself between objects that's stretching. So
well, obviously the best comet we've had in perhaps many of our lifetimes was comet Hale-Bopp. Lovely picture here showing the dust tail and the wonderful iron tail. A few more pictures of it there. I took a picture of it. We were using our Lovell telescope to study the gas in the tail. So hopefully that it should be looking towards the comet. And I was out there that evening.
It's the oldest example of this type of Kepler observatory in the world. And if we go inside, you can see the original wooden construction of the dome, which is still there, but the telescope picture here isn't actually the original telescope used to observe the transit. And after a bit of research, I managed to track it down, and it was a telescope that looked something like this. This is one that was displayed in the British Science Museum. It's a 4.5-inch reflecting telescope.
So what we're seeing is at the moment 24 seconds, 28 seconds, so it's got 7 exposures, and then it will count up and up.
Okay. And it will continue to keep
stacking. It will continue to do this. It will stay absolutely focused onto the object.
Here we are inside the observatory. You can see the telescope already lined up. Oh, wait, have you got a picture there?
Yeah. Mare Crisium is on the.
Can you see? We have a. Oh, that's a really good image. Right. Well, that looks encouraging for later on.